Let me start the class. We are discussing about transmission line theory. So far now, what are the things we have discussed, and let me give a little summary about that. Then we will go to the topic. Today I will complete the class very quickly, and so the next few classes we will discuss about the very important topic in transmission line theory, that is the Smith chart. So that onwards we will go ahead. So today I will conclude the previous part of the transmission line theory, that is how the input impedance is calculated and the reflection coefficient are described for a transmission line of length L. Then there are some special cases like open circuited, short circuited lines, and lambda by 4 lines, and lambda by 2, lambda by 8 lines are there. So we will see how this impedance or impedance function of these lines are uh, described mathematically, as well as how this used in practical aspect that we will discuss. So we already know that the transmission lines are nothing but guiding structures for a high frequency signals which are traveling. Normally it will travel in very high speed with means in a straight line it will travel, and if we allow that to go in a wireless media, that is without any uh, without any guiding path, if we allow them to transmit for a distance from transmitter, let's say we are transmitting from one place to another place by two antenna, they start to go. But the very important problem is I am sending around some, let's say 10 watt power I am giving, but how much power it will go, if you see with respect to the amount of power in terms of an angle, just about 1 degree of the total power will go there, which is, we could say that it is approximately 1 per 360. So in order to receive some decent power at the receiver side, if we call that power as a PR, then this power, if I want to get more, I have to increase this power about at least 360 times we have to increase. This is one minor drawback in wireless system. So this is always a limitation for a wireless system, but there are some interesting benefits are available. We will discuss maybe in the upcoming classes. So this is one minor drawback, and as well as the distance increases, this radius also, as this value increases, this angle value also will keep on decrease. So this is one of the important problems. So and moreover, this is not a secured one. So if I keep some other transmission, another antenna, very similar antenna, if I keep, I can tap it. So this is completely unsecured system. But there are plenty of benefit that the system can move, which we call mobile. So there are some other benefits are there. So we're supposed to see what type of application, whether security is needed or not, or all these aspects. The transmission line, which are going to give a guiding structure for the wave propagation. So instead of a wireless, if we give wired transmission, we can at least save the power. For instance, if we give 10 watt power for a low loss transmission line of alpha, very low value, we can even get around some 8 watt power here. So we could save the power a lot. But we're supposed to keep physical line. Physical line is made up of metals and some dielectric materials, and as well as encapsulating layers. So this obviously this go uh, costly, and it is also fixed one. So then there will be a question will come, so which is how to be used for what application. So it is very easy that if you take a let's say you are having a mobile system for a city, and the city has one tower. So this tower has an antenna, and you have your mobile phone. So from here to here we can transmit over wireless. So but the internal systems like antenna to the base station, mobile, within the mobile, antenna to chip, within that system, we could use transmission lines so that we can save the power. And so in other words, we can say that in order to construct some building blocks of the high frequency systems, we can use the transmission lines for communication purpose or for moment applications, mobile applications. We can use wireless system. So it's kind of a debate all the time. So I have some concluded in this aspect, but there are people having different different conclusions on choice of transmission lines and wireless systems. So this all will come by means of experience. Okay. So we can't simply tell that the transmission lines are not useful in the future, but in future we could say that transmission line could be used even in various levels. For example, optical fiber is a type of transmission line which carry another type of electromagnetic wave, that is nothing but lights. Okay. So there are equivalent structures are available. So it is worth to study this important theory. In the next upcoming semesters, we will study this transmission line theory's advanced version as a microengineering. So in the leftover classes, I think around some 2 classes will be left over. I will give you some idea that how to construct some microwave systems using this transmission line theory. So we discussed a lot about how the wave travels in a guided structure, in a encapsulated metallic structures, how the wave travels, what are the different modes are available. So you need not to remember those all things, but it is very mandatory that all people supposed to at least get introduced to that. In fact, these theories are not available in your syllabus. And this wave propagation is defined in terms of alpha and beta. It is like very same as that of how the wave travels in a medium. Here in guided structure, in this type of guided structure also, how the wave travels, that can be defined. And this alpha and beta defines, there are 2 regions. One is attenuation region and propagation region. So attenuation region means those frequencies won't be allowed for wave propagation. So low frequency signals won't travel through this, should not travel through this structure. And for example, we have seen a waveguide system, alpha and beta, how it defines. And so this wave propagation theory supposed to be constructed upon a guiding structure. So for this, we supposed to come up with the model for a transmission line. So that is where the transmission line theory comes into the picture. So the ultimate goal of the transmission line theory is twofold. One is getting the equivalent RLC, so that I can directly apply this RLC equivalence for a circuit theory. We very much aware of the circuit theory, even solving the real and imaginary part based concepts. So in that way, we can easily solve the transmission line concepts also. And the second important fold is explaining the impedance of the transmission line in terms of its length or the position. So if it is traveling along the z direction, so at any particular point, we are supposed to be in a position to calculate the impedance of it. By the way, if you define that, you will get once again the real part, imaginary part will come. So the advantage of having this is we can apply the maximum power transfer theorem. I think all of you studied about maximum power transfer theorem. It says that the load impedance is supposed to be equal to source impedance. So here the source is connected to the load by means of a transmission line, which is having its own alpha, beta, and the very important thing is characteristics impedance. So this is going to define that. Now, since the length of the line is coming into the picture, obviously the impedance will change. So if the impedance is changing, then how to make the maximum power transfer? If I give 10 watt power, I supposed to get at least 9.5 watt power here. Whether it is possible or not, yes, it is true, it is quite possible. And in fact, the 0.5 watt here is simply gone by means of the loss of the transmission line, because we are not using a superconductor, we are using the conductor with finite conductivity. Obviously, there will be some loss, some dielectric loss will be there. So this is the overall twofold means the requirement for a transmission line theory. So that is where the modeling into RLC equivalence are coming into the picture, and we have applied the simple RLC equivalence of the voltage and current in terms of Z and T, that is time, and naturally we will get the exponential terms with the resonant means angular frequency will come, which is nothing but 2 pi f. So by this way we can easily separate the z term, that is space term, as well as time term. So this is the basic idea, and after that it is very simple. We will easily get the wave equation, and solving that we will get the alpha beta in terms of the equivalence RLC, and the impedance also in terms of its equivalent RLGC. So by the way, the first fold is completed, that is defining the primary and secondary parameters. These are primary parameters. The RL, GC are secondary parameters. So now this is the first one we have done. I believe you have seen some examples also. Now we can't argue that all the lines are lossless lines, because obviously alpha will be finite value. It cannot be zero. But we can make the line distortion free line, which is very much useful for communication application. I think we extensively studied that. We'll skip this part now. So first part is completed. The second part of the transmission line theory is nothing but defining its impedance as a function of the position or the length of the transmission line. So how to do that? So for this we have taken a setup. In this setup we have a source and a load, and both are connected by means of length of transmission line with length L, and whose alpha beta are given in terms of gamma, and its characteristics impedance are available. Characteristics impedance is given. So we have about 3 parameters for the transmission line. One is okay, in fact we will put 4: alpha, beta, z0, and the length. Okay, these 4 values are important because all of them are going to vary the impedance of the transmission line for the given load impedance. Now we are going to say that we are exciting the transmission line. Exciting in the sense we are giving input signal. So the input signal is going to be Vg. That signal is giving a terminal voltage of V0. So V0 is, you can say that at the initial point when z equal to 0 point. Okay, and it is going to have a current of I0 also. We can easily calculate the value by means of calculating its input impedance. By the way, we can easily get the initial voltage and current, and this initial voltage and current going to propagate as a wave in the transmission line, and considering the factors of alpha, beta, z0, and over the length they are going to travel. At the end, it is going to see a load, and this load impedance, we could say that this is a kind of a boundary condition where this transmission line has the impedance of Z0, and this medium, it can be a medium or system like that. So it is having eta of ZL. So both the impedances are different. So obviously there will be a reflection will takes place. So this reflected signal will come back and will be available at the same particular point. For our convenience, we are going to take alpha equal to 0 so that no loss during the wave propagation. So obviously we have 2 systems. One is incident wave, we can call that as a plus, and the reflected one, which is nothing but V minus. You're supposed to remember that the exponential terms always given with negative for forward signal and positive for reverse signal. So this is slightly you have to keep in mind. It's not very complicated one. In fact, without this exponential terms, we can solve so many problems. So by the way, the voltage and current at any particular location of the Z can be described by means of the summation of incident and reflected component. So what is the meaning of that? You take any particular point. If you want to calculate at any particular point, you want to calculate the voltage and current. What you have to do? You have to add the incident component and the voltage component, and the incident component and the reflected component. You are adding because the voltage, there is no polarity for it, but in case of current, they are actually forward going current, reverse going current will clearly show the difference. So it is nothing but the difference between that. So this is the very fundamental equation which describe everything else. Okay, so by the way, we have clearly defined that at any particular point, the voltage and current is nothing but summation of incident and the reflected component, or forward going signal plus, in fact, they are nothing but solutions. I could say that it is already solved here. So we already got here. Okay, so therefore the equation is very much valid. So we are taking this valid equation and we are going to calculate the impedance at any particular point. So for this, we have to isolate this incident component and reflected component. It is very simple that if you add this two equation, so you will, when you add this two equation, you will get, you can remove this part. When you subtract, you can remove this part. So by the way, you can see that we can easily get the V0 plus and V0 minus. Now we got two incident and reflected component in terms of the voltage what we are giving as the input here. And once we know that at any particular before going to get at any particular point, we are defining what is the same voltage available at this load point. So which is going to be, so this Z we are going to make it as L. So by this we will get incident and reflected component can be easily arrived. And what is this VL and IL is nothing but the voltage and current at the end of the transmission line. So which can be, the ratio of them is going to be nothing but impedance. So ZL is nothing but VL minus IL. Both are complex numbers. Okay, so there will be a real and imaginary part will be there for both voltage and current. Now we can easily calculate the input impedance at any particular points because we have described the voltage and current in terms of its position, and both are complex numbers. So obviously you will get impedance only. So we can easily get it. So we have taken this. I'm sorry. So this term, it is presented here. Okay. So now once again we are substituting the incident and reflected component in these two equations, and there will be a little lengthy derivation will be there, and because this exponential term will convert itself into tan h and you will get like this. So this is the input impedance at any particular point. So there are plenty of advantage we have to define this equation for a transmission line, because I want to ultimately get the maximum power to be transferred. So at this particular point, so this is going to be the source, this is going to be the load. So at this particular point I calculated the input impedance. What I simply supposed to do, I have to make this equal to ZS. So by the way, I can transfer the power to here maximum, and it will travel and it will give the maximum power to the load. That is what ultimately we want for a communication system. And so to define that, we are having input impedance. To describe the power transfer, we are actually having this reflection coefficient, which is very same as that of the boundary condition based, which is having eta 1 and eta 2. So the reflected component will be having a coefficient that is called reflection coefficient, which is nothing but eta 2 minus eta 1 divided by eta 2 plus eta 1. So that is what actually written over here, and this is at length z equal to length L, and this is at any particular z point we can calculate the reflection coefficient. So when you say that z equal to 0, which is nothing but the initial point, you can easily calculate the input reflection coefficient. The input reflection coefficient is nothing but input impedance minus Z0 divided by the input impedance plus Z0. You can easily calculate the reflection coefficient for a given transmission line, which is ended up in a with the ZL. So we got it. Now this is actually one type of representation of the incident and reflected component by means of your coefficients. So this reflection coefficient gamma L or gamma in. So they are actually going to define how far the source and load are get matched, whether the maximum power is transferred or not. That is described by this gamma L and gamma S. Let's say if this value equal to 1, gamma in equal to 1, the meaning is the V naught plus is equal to V naught minus. That is the meaning, is it? So according to this, if you say this value equal to 1, so which is nothing but the magnitude of the gamma in is equal to magnitude of this. So in other words, what is the meaning is whatever the wave is transmitted inside a transmission line, all of them get reflected, nothing going inside that. But if we make the value equal to 0, what is the meaning is there is no reflected component. In other words, all the incident component went as a transmitted component. So all the signal gets transmitted inside. The reflection coefficient naturally become 0. And there are intermediate values. If we get 0.1, 0.2, 0.3 up to 0.9, which means that partially the reflection is taking place, partially transmitted in. So this is what the meaning out of that. But in but there are some other influencing factors available, so they can describe the same concept of reflection or the reflection coefficient in other means. So that is described by the traveling wave, which is forward wave, and the reverse wave. Both actually will add each other at a given time and position. So with respect to the position, sometimes they add each other, sometimes they subtract each other, add each other, subtract each other. So they will be defined by maxima and minima of the standing wave. So standing wave is nothing but the forward wave plus the reverse wave. So that is nothing but standing wave. And this V max and V minimum describe the magnitude of the overall reflection. Let's say there is no reflection, then what you will get is no wave, almost everything will become maximum. And there is no so we can't argue upon that there is no incident wave. So the question is, if the reflected wave is half of the incident wave, so the reflected one is half of that. So which means that this magnitude also will come half. So V max will be equal to approximately half of the V minimum, because half of the wave is cancelled out. So that is what will happen. So by the way, we can define the reflection behavior by means of this V max and minimum. This ratio is voltage ratio, is often referred as voltage standing wave ratio. So often referred as VSWR. Similarly, ISWR is also available. And so this is the ISWR, this is VSWR, voltage standing wave ratio. And this is the equivalence for the standing wave ratio and the reflection coefficient. So by defining a transmission line of having we have a transmission line which is connected with the load impedance and which are given with the source, and there is the incident wave that is nothing but V naught plus. So this is actually traveling upon that. The traveling is defined by alpha, beta, and the Z naught and the total length L. Okay, these all things going to define that. And it is getting reflected and coming back, and this is where we have a V naught minus. So the input reflection coefficient is nothing but V naught minus divided by V naught plus. So by measuring this, we can say that whether these two source and drain, they are in the maximum power condition is achieved or not. So this is often referred as matched. When if it is equal to 1, that is actually mismatched. And when this is greater than 0 and less than 1, they are actually partially matched. So this is going to describe the maximum power transfer effect using this transmission lines. So this interestingly, 90% of the work was overall completed by Heaviside himself. He has described all these things in his notebook, and he also published as a textbook also. For many universities, still people are following that. We got it, and we have also seen some examples of the cases. So we have a transmission line whose impedance is given. If you notice that the characteristics impedance will be always, or 90% of the value will be having only real term alone will be there. So it will be defined as 50 ohm, 60 ohm, 75 ohm. So 50 ohm is the most popular one. We will see in the next class that why it is popular. And it is having length of L with 30 meters, and it is operating at a 2 megahertz. So what is the meaning of that? I am having this is the transmission line, and I am having a, let's say, transmitter. This transmitter is operating in 2 megahertz. So that signal is traveling in. So this signal is, we supposed to deliver this signal to a load after 30 meter, whose impedance, it is, we can say this is a telephone. So I used to draw like this. So we have a telephone. So this telephone is having its own load impedance. This load impedance is given over here. Now what I have to do, this exchange, the telephone exchange, supposed to transmit the maximum power from here to here, and here to here it's supposed to come. Okay. So this is the, this seems like very simple problem, but it is very, very tricky problem, because it's supposed to be matched all the time. If, let's say, this transmitter is having ZS, and this is having Z0, and this is having ZL, they are not matched at all. If they are not matched, what will happen? Whatever the signal which is supposed to come to us will be completely reflected back. Nothing will go to the receiver. We can't hear anything else. You can even try that. So what you can do is, if you have physical telephones in your home, you can just make some cut in the transmission line. There will be 2 wires will be there, but it is very risky to do that. So you just cut this and put some capacitor or something else. So immediately the impedance will collapse, and you will see that you can't receive anything. There is a possibility that you can receive somebody's call. Okay, that is what we call tapping. So somebody will put this, and they will make some changes in the impedance, and they can get somebody's signal. So that is quite possible. You could see that such a tapping telephones will be completely different looking, which with some big structure naturally. Will be having some tuning networks inside, and the phase velocity is given. So this phase velocity generally people used to give in order to indirectly define the beta. So, and it is a lossless transmission line, so obviously alpha equal to 0. So first we have defined alpha, beta, and Z0 is given, and length of, so all the important properties are given. So obviously our important job is to calculate the reflection coefficient, input impedance all the way. First, the load reflection coefficient is calculated using this very simple equation. So this value is not equal to 0, which means that it is not matched. So when this value will become 0, this value is supposed to be equal to 0. Sorry, in order to get matched, this value is supposed to be 0. And alternatively, this same gamma L can be defined in terms of standing wave ratio, S. So using this formula, it is calculated. So this value will be generally greater than 1. Next, we have calculated the electrical length of the transmission line. So we already know that beta is nothing but omega by B. Omega is nothing but 2 pi f divided by U is given. So by this way, you can easily calculate the beta value. Now, what is this beta L is nothing but the equivalent length or the electrical length. This total length 30 meter. This look like this value is a fixed value, but in terms of operating frequency, considering the wavelength, so there is multiple wavelength can be accommodated. So to define that, people have come up with the idea called beta L. So this is going to define the electrical length. This will be often referred in terms of degrees. So here it is 30 degree. Next, the this beta L is often used in many places. because if you see the so-called the impedance, here you can easily see that tan H gamma L is there. What is this gamma L? Alpha L plus j omega L, sorry, j beta L. So this beta L is often referred. Alpha L is subject to question that this value may be 0 for lossless transition. So, but beta L cannot be 0. It's supposed to be there. So that is why people always calculate beta L. And since it is a lossless transition line, so we are going to substitute this alpha L equal to 0. So you will get tan H j beta L, which is naturally nothing but tan beta L. So that is what we got here. And this imaginary part has come brought into the front side. So that's the equation. We have to solve it. We have ZL. We know Z0. Beta L is known. So by substituting all the value, we can do that. This calculation is supposed to be very crucial. Crucial in the sense many people do it by casual means. So don't do that. Always calculate the tan beta L first, because this value need 2 times. Then you put, then you reduce. So slowly you do that. For instance, here it is clearly done that slowly, which been reduced, and most probably you can avoid you can avoid some mistakes here. Finally we calculated the input impedance. So this input impedance, we can use it to calculate the reflection coefficient. So that we can do by means of this. So you take the magnitude of the input impedance, that is 24.01 minus Z0, that is 50 ohm, divided by summation of that 24.01 minus 50. So this is approximately it is nothing but minus 25 divided by 75. Sum Alice number. So this is actually 1/3 of that. In other words, 1/3 of the power get reflected. So that is the indirect meaning out of that. So this is the meaning of this workout. So I have given some physical example with telephone exchange and this one. This can be modified into, like, there is a chip. This is a Qualcomm chip, and they are nothing but that is having transmitter receiver, which we call transceiver. So this is going to convert all the modulated, demodulated signal, and this is given to an antenna. This antenna going to transmit the signal. So this is your mobile phone. So in the back side of the phone, you will having almost all the microwave systems which are used for transmission purpose, all the internet, everything else connected with this. And in the other side, you have the display. Everything will be the keypad, everything will be available. So if you open the mobile phone, you can easily see that. If you have very old mobile phones in your home, just break it. Nothing wrong in it. So this is so here where the transmission line is coming. Now these all theories we have seen. Now we are going to apply some special cases. So if the transmission line is ended or terminated by a short circuit. What is meant by short? This means that we are going to connect this positive end by means of a wire to the negative. Okay, so by means of a shortest line, we are going to place it. So this is a complete. So which means that all the incident component going to travel and will come like a reflected component. So this is often referred with the ZL equal to 0. So this ZL equal to 0. What we will get. So we are going to substitute this ZL equal to 0 here, this ZL equal to 0 here. So if you substitute that, this entire term will go and this term will go. So you will get Z0 by Z0. So this two term will cancel each other. So you will get Z0 tan beta L. And if we say it is a lossless line, so alpha equal to 0, you will get this. So ZC is nothing but J Z0 is, if you say this equal to JX, which is nothing but a reactance, you can notice that there is no real term. So always a short circuited line will be not having any real part, and most probably it will be having reactance term. Okay, and this is quite similar to that of J omega L. Okay, so J omega L is nothing but inductance. So most of the short circuited line will behave like an inductor. So you could notice that this impedance function this impedance function ZSC, when you plot with respect to beta L, what you will see that the beta ZC value will go positive until this pi by 2. Pi by 2 is equivalent to lambda by 4, which means the length is lambda by 4. And after this lambda by 4, after slightly there is an increment, it will go to negative value. Just it will completely invert itself and you will get negative value. So this negative value is nothing but minus Jx. Minus Jx, when it will come 1 by j omega c. So you will immediately get the capacitance behavior. So this is the interesting factor. So most probably what people used to do, they will take a transmission line of length equal to lambda by 4 and they will short circuit this by simple wire. So what you will see as an input is nothing but j omega L will come. So it can be used as an inductor. So wherever you want an inductor, you can use a short circuited line. And this always has the reflection coefficient of -1. This because all the positive is connected to negative, and you will get the so-called the input impedance is nothing but 0 minus 1 divided by Z0 divided by 0 plus Z0. So you will get -1. So many people used to miss this negative term for short circuited line. This is very, very important term, so don't miss it out. And VSWR, if you take, it will go to infinite, which means that all the signal will come back and this ratio will naturally go 1 by 0, which will be infinite. So this is the property of a short circuited line. And what about open circuited line? The open circuited line is nothing but we are having a source and there is a transmission line. This is completely open, nothing else is connected. This positive and negative is still not yet connected with anything. So there is nothing else is there. So at that case, we can call that is nothing but infinite impedance. So that is why no signal is going away. So in this case also, whatever the signal is coming will be reflected back. So you will get a special equation. So you will get the denominator will be having this reactance part. So you will get negative sign. So I already told that this is equal to 1 by j omega c, because this 1 by j omega c will give negative term. So that is why the capacitive behavior will come. So if you take a transmission line of length L, so you will get capacitive behavior. Once again, if you take a open circuited line of lambda by 4 or lambda by 8 or something, then you will get capacitive behavior will come. So let's say I want to make a RLC network. So I want to make a series resistor and a capacitor and an inductor I want. So it is very easy. You take a resistor and put a short circuited transmission line and a open circuited, this is actually capacitor. So this is very much equal to a resistor with, this is an open circuited transmission line. So we are going to take a open circuited transmission line and a short circuited transmission line. We are going to take a short circuited transmission line, and so this is the lambda by 4 length. This is lambda by 4 length line. What is this lambda? Lambda is nothing but C by F. Approximately, I should say C by F. So I have a source with operating frequency. This is my carrier signal or something. So this signal will get equivalent capacitance inductance by means of this transmission line. So we can easily construct almost any circuit with this transmission line. So we will see in future that while we use high frequency signal, it is very difficult to use this kind of lumped RLC. But naturally it can be done with the transmission lines. So we can construct many things like filters, amplifiers, wherever this type of reactance or reactive elements is needed, we can very well use this transmission line. So that is what I say that in 2 classes I am going to teach the application of the transmission line in microengineering. I will show something like that. And very final, very important one, that is called matched line. So the line will be matched when we say that the ZL equal to Z0. What is the meaning of that? I am having a transmitter ZS and it is connected to a transmission line which is having a characteristic impedance of that, and which is having a load impedance. If I put this Z0 value, ZL value equal to Z0, okay, this is having 50 ohm. Then I have a telephone which is having a ZL equal to Z0, which is also 50 ohm. If you make such a thing, then maximum power will be transmitted. So you will get the reflection coefficient 0, standing wave will give the lowest value of 1, and what is the benefit of that? You will get 0 reflection coefficient. And this is studied in many places. This being studied. This is a simple example that if you make such a load impedance equal to characteristics impedance, what you will get is you will get the reflection coefficient. In terms of dB, it is given. I will tell the reason why it is so. But if you see that this 0 dB is equal to 1, and this value is going to very low value of 10 power minus 40 divided by 10 power minus 4 approximately. So this value is approximately equal to 0, very low value. While comparing 1, this value is very low. So which says that the reflection coefficient is 0. If the reflection coefficient is 0, what is the meaning of that? The signal is going from here to here. There is no reflection. But what about here? All the signal is getting reflected before reaching the load. So this is giving a selective transmission to a load. So for a given load, only certain range of frequency alone will be allowed. Remaining frequencies are not allowed. So this is a very interesting thing, that I can properly send a signal within this so-called bandwidth. This bandwidth actually derived out of the reflection coefficient, which is derived out of the impedance. So that is why this bandwidth is often referred as impedance bandwidth. So this is what the interesting advantage of a system. So assume that I have a transmitter, I have a receiver, and both are tuned for a particular frequency. We call that as the operating frequency f0, and the transmission line is matched in such a way that it is operating at this particular frequency f0. So a secure transmission will come. If somebody want to get the signal, they're supposed to get very similar operating frequency. So this is how the radio station works. So you have to tune to this particular frequency. So what is actually happening? Yeah, load is nothing but your radio, and the antenna is there. Antenna is having some impedance. Let's say this is some X. Both are connected by a transmission line. So here what we will do is we will make a inductor or capacitor will be there. So by means of tuning it, I can match this ZX with the ZL. So maximum power will be transferred. So this exactly will be done for the operating frequency. So if I tune for some other capacitor, I will get different station. So this is the very important trigger point for the communication systems, for a secured communication system and multi-band communication system. So multi-band communication systems will be having multiple minimas like this. So within this very narrow bandwidth, people used to have multiple. So what is this is user 1, user 2, user 3, or you can say this is TV channel 1, TV channel 2 in a same cable or in a same DTH system. We can get that. So this is what the interesting fact behind the microwave system. In the advanced, this is a completely advanced microwave system. It is very difficult to make it because you're supposed to make it very clear. There should not be any inter-channel communication between them. So this come what crucial ones. And the most important concluding remarks in the transmission line theory is often referred as quarter wave lines. So this quarter wave lines are the transmission line of length, which is having lambda by 4, has some special advantage. So what is that? So we are going to take the transmission line which is terminated by a load, which is nothing but RL, and we are going to calculate the input impedance for the length of L, let's say. So it is having alpha equal to 0, lossless line. So this is the equation for it. Now we are going to have characteristics impedance is Z1, so that is why we got like this. Now this we are going to substitute the special case, that is lambda by 4, a quarter wave line. So if you substitute that, you will get beta L beta L is, I already said that beta is nothing but 2 pi by lambda, and L is nothing but lambda by 4. This 2 will cancel, you will get pi by 2 will come. If it is pi by 2, tan beta L, tan pi by 2 will become 0. So if it becomes 0, this entire term will be gone, and it is, this actually infinite will come. So if it is infinite, this entire term will become infinite. Then infinite plus 1 or infinite plus RL, whatever it is, that's once again goes infinite. So the entire term go meaningless. So what people generally do is they will try to put it in the denominator. So how to do that? You just divide the entire term, numerator and denominator, by beta L. So you will get like this: Z1 RL by tan beta L plus J ZL divided by Z1 divided by tan beta L plus JRL will come. So now when you substitute beta L equal to infinite, this term alone will go 0. So by this we can get the remaining part. This is 99% correct. So you will get this special equation. So for a quadrature transformer, the input impedance is nothing but characteristics impedance square divided by the load impedance. So that is nothing but the input impedance. Now if I want to get the input reflection coefficient equal to 0, what I am going to put? I am going to substitute the equation. So you will try to simply put Zin equal to Z0. So that is the condition. So when you substitute this equal to Z0, so what you will get? So this is the Z0 value. So you can easily calculate out of this Z1. So how to do this? This RL you bring this side, square will become root this side. So you will get this. So what is the meaning of that? Is I have a load with ZL and I have a source, let's say with ZS. I have to match this two. So how to match it? So you take a transmission line exactly of lambda by 4 length. So how to get the lambda by 4 length? I already know the frequency. So C by F will give the lambda. Lambda, say it is some 10 meter. So 10 meter divided by 4, you will get 2.4 meters. So you take a 2.4 meter transmission line, and whose impedance is Z1. So that is what it is calculated here. So this can be easily calculated, is it? So this value, let's say something 50 ohm. Z0 is 50 ohm. This is nothing but 100 ohm. You just multiply and take root of that. You will get the value. So when you take such a transmission line, it will be matched perfectly. So you will get maximum power will be transmitted. So this is the primary benefit of having this lambda by 2 line, shortly referred as quadrature line. And this is going to transform the impedance from ZS to ZL. Smoothly it is going to transform. So that is why it is often referred as quadrature transformer. So this quadrature transformer will give ready-made matching. In fact, it is going to give a matching for such a large bandwidth. So you will get the reflection coefficient for a system will be like that. What you are going to do, you are going to send a signal with operating frequency. This frequency can be varied from 0 to such a high frequency, and they are divided by F0 to have a normalization. So this is nothing but F0. This is 3F0, like that. So there you will get the minimas. So they are nothing but harmonics. Okay, so this is how the system works. So this will give such a beautiful matching, very easy. For example, this is often one of the most commonly used antenna in mobile phone. So the mobile phone is made up of a PCB, which we call motherboard, which is having a dielectric material of the dielectric constant of this. It is having a ground plane and a top plane, which we call conductor. This is called ground. Okay. So what people used to do is they will cleave some area to make it as an antenna. And here you are going to have a chip. Your transmitter chip or receiver chip will be there. Both are connected by a transmission line. So how to have a best matching between these two? Because transmitter, a microchip or a nano chip, it will be operating in different impedance. Let's say ZS. This antenna, we are having this antenna impedances and ZA. Now we have to match it. So quadrature transformer is very well available to match it. So first we have to calculate the input impedance at this particular point. Then we very well know the impedance of that. Let's say it is a 50 ohm line. So both should be matched. So I am going to use a quarter wave transformer. So this quarter wave transformer, when I use, I will get the maximum power will be transmitted. So this is the simple idea. This is the antenna. This is the feeding line or your transmitter line. So this is the quarter wave transformer. So this is actually simulated one, a tool called HFSS. If time permits, I will teach that. Then this is a fabricated one from this. So what you see in the top surface is the top side of the PCB. The bottom side is still ground plane. So now what we are going to do, we are going to send a signal at frequency F, and we are going to calculate the reflected component. So we are going to have V plus, V minus. So V minus by V plus is nothing but the reflection coefficient. So it is plotted with respect to dB. You can see that exactly at the desired frequency we got the best matching. So this frequency is nothing but 2.45 gigahertz. Do you know anybody that what is the specialty of this 2.45 gigahertz? Nobody knows. So this is the operating frequency of the Bluetooth system. Okay, all the Bluetooth systems are using this exact frequency. So what you see is the Bluetooth dongle antenna. So the entire Bluetooth dongle, I think many of you know that the Bluetooth dongle will be having some USB port here. Then there will be a plastic encapsulation will be there, nothing complicated. This multiple pins are given to a system which will make everything in a single multiple frequencies within this band and will be given to a antenna. So this is the antenna what you see here. This will radiate, and your mouse or something else will be operating in the same frequency, can be connected. So this is what the entire concept. So you could very well visualize that how this transfer line theory significantly improves the communication system efficiency of work transfer. So I will end up this concept here, and now the advanced matching techniques we are going to see in the upcoming class. So that is nothing but single and double step matching network. For this we have to go with the idea called Smith chart. So in the next class I will teach the Smith chart, and so this will take around some 2 class, and this will take 2 class. So 4 class I will complete. Remaining I think we have 3 more classes we will review for FAT exam all the way. Have any questions or any doubts or your experience in transmission lines or anything else you have?
Excuse me, sir.
Hmm.
Sir, I wanted to ask about the quiz. Sir, is it possible to give it on Monday? Because